In a previous video, I had mentioned that in two-dimensional motion, it's entirely possible to have the velocity and the acceleration of an object point in pretty much any which way that you would like. The piece of the acceleration that is either parallel or anti-parallel to the velocity is associated with the change in the speed of the object, and the bit that's perpendicular to the velocity is responsible for the change in direction. It's that latter part that I want to treat right now, so we're going to go ahead and figure out what we usually call the centripetal acceleration, the piece of the acceleration that's pointing perpendicular to the motion or towards the center of a circle. So I'm imagining I've got an object that's going around a circle like so, at speed v, and I'm having it go clockwise. It doesn't matter if it's clockwise or counterclockwise. And I want to know the magnitude and the direction of the acceleration right at this very top point here. But in order for me to figure that out, I'm going to have to look at a point a brief period of time before and an equal period of time afterwards. And the game will make the time intervals ever shorter and shorter and shorter, eventually turning our finite differences into differentials. All right, so first I need to find the velocity at the midpoint here. And so to do that, what we'll do is we'll go ahead and find the average velocity for this interval here, and then we'll repeat that over here. So to get the average velocity for this interval, first thing I need to do is get the displacement. So let's go ahead and do that. Oops. So so if I look at the interval from 1 to 2, my final is R2, like so. And my initial is R1, but I'll be adding negative R1 to that. And so I get that here I use the tail to head rule, that the change in the velocity over this first time interval, so I'll call that delta R1, points like so. If I parallel transport that back here, no big surprise, that's just taking it from here to here because, hey, that's the displacement. Okay. And similar, we can do exactly the same thing to get the displacement for this interval here. That's delta R2. All right. Now, the deal here is that my delta R1 points up and to the right, my delta R2 points down and to the left. So I can draw corresponding vectors v1 and v2 that are parallel to my delta R1 and delta R2 because I'm looking at equal time intervals. And remember, the average velocity is the displacement over the time. But I can use this to find the change in the direction. I can use this to find the change in the velocity, and from that I can get the direction of the acceleration. So we'll go ahead and play the same game here. We will go ahead and draw a v2 like so. I'll add to that negative v1 so I can find my final velocity minus my initial velocity, so the velocity before and after the time I'm interested in. So there's negative v1. And so delta v, the change in velocity, points straight down, it turns out. Cool. Now, with a little bit of fiddle-faddling, actually, pardon me 1 second here, and since delta v points down, since the acceleration is the change in velocity over the change in time, so multiplying by 1 over the change in time is a positive scalar, that means the acceleration points the same way. So we get at this point right here that the acceleration points into the center of the circle. And there's nothing particularly special about this exact point that I chose. I could have repeated this for any point on the circle, and I would have gotten the same result, that the acceleration points into the center of the circle. Now, if we do a little bit of geometry here, these two angles are congruent by construction because I said these are equal time intervals and we're going at a constant speed around the circle. So we cover the same arc length in the same amount of time. So by definition of an angle being arc length over radius, these angles are congruent. You should also be able to convince yourself that this angle is the same as that angle. And because my velocity vector, my delta r's here, and you should also be able to convince yourself ultimately that this angle is also congruent to all of those angles. And this is just because instantaneous, as we go to smaller and smaller time intervals, what we'll find is that our velocity becomes tangent to the curve. In fact, it's looking at a point right here. So we split this, split that. That's that angle there. My velocity vectors are perpendicular, so that carries the angle through there. Now what that lets me do is it lets me say that this triangle, this vector triangle here, and this vector triangle here are similar triangles, so I can set up a proportionality. I can say that delta V is to either of these V's because V1 and V2 are both the same, so I can just say delta V over V. I can say that that is the same difference as delta R over R. That those proportions have to be the same by similar triangles. Okay, now we know from from our definition of acceleration, it's the time rate of change in the velocity. And yes, this is technically an average acceleration, but don't worry, at the end we'll take a limit as delta t goes to 0 and everything will become a derivative, so it's all good. So I can rearrange this to get that delta v is equal to a delta t. So I can go ahead and stick that in there. So I get that a delta t over v is equal to delta r over r. Now, here's where I need to cheat just a little bit. This length right here, from here to here, that is the difference in arc length. And I am going to say that my a delta t over v is approximately equal to my arc length delta s for that interval over the radius. Now at first that looks really bad, but it's actually okay. And the reason it's okay is, remember, at the end of the day here, we're going to be taking our time intervals down to approaching 0. So if I look at a sequence of chords that I strike off against my circle here, the arc length and the radius don't look anything like each other. Here they look more like each other. Here they look more like each other. And in the limit of smaller and smaller periods of time, the smaller and smaller angles, the arc length and the radius approach each other. So it's all good, given where we're going with it. So I can go ahead and rearrange this to get the acceleration then. It's going to be equal to v over r times the time rate of change of the arc length. And here I can go ahead now and take the limit as delta t approaches 0. And in this limit, this is going to become a derivative. But the point of that is for me to realize that this is also the speed I'm going. So we say that the magnitude of the acceleration, which we call the centripetal acceleration, is equal to v squared over r. So we say this is the centripetal acceleration. And centripetal is just, if you break the roots of the word apart, just means center seeking. So this is the piece associated with changing direction. It's not associated with changing speed at all. Now we could have also said that that we were going around with angular velocity omega. So if we remember from the last video, we had that our tangential velocity was equal to r omega, which is just v. So if I put that in, I can get another expression for the centripetal acceleration. V squared will be r squared omega squared over r, cancel. And I get that an equally useful expression is r omega squared. And again here, just to look at units, for an acceleration, we're expecting meters per second squared. Radius is meters. This is radians per second, is our omega. But we're squaring it, so we have to square the units. Again, remember that radians squared, that's going to be the same thing as 1 squared, which is the same thing as 1. So then we do indeed have meters per second squared, and it all checks. Remember, radians are not a unit. They are a symbol that reminds us that we're dealing with an angle, but it doesn't have an actual physical dimension. Okay, so just to maybe make this a little more concrete, let's say that we've got a mass going around on a string. Like so. Let's say that we are going at, well, let's say 2 meters per second. And let's say our string has a radius of 50 centimeters or half a meter. The acceleration, if we're going at constant speed, it will accelerate because as we go around the circle, the direction of the velocity will keep changing. So the acceleration is pointing to the center of the circle. And the magnitude of the acceleration here will be the centripetal acceleration because we said we're going at constant speed. So it's v squared over r. So this will be 2 meters per second squared over half a meter. We're going to get 8 meters per second squared. So even though an object is going around, moving at constant speed, if it's changing direction, it is accelerating because velocity is both velocity has both a speed and a direction. Okay. However, it is possible that we could be picking up speed, and so to that end, we want to think about how rates of rotation could be changing. So we'll go ahead and define angular acceleration. And just like we had said before with translational acceleration, that it was the time rate of change or the time derivative of velocity, this will be the time rate of change or the time derivative of angular velocity. So the symbol is a lowercase Greek alpha. So this will be the limit as our time interval approaches 0 of the change in the angular velocity with respect to time, or we can write that as d omega dt. And our radian units will be radians per second squared. And remember, radians don't have an actual physical dimension. Same difference as writing the number 1. And this symbol here is a lowercase Greek alpha. So just to go ahead and draw that, like that. You do something like that. Basically, you're just drawing yourself a fish, but you resist with all of your might to finish off the fin and the face and the little bubbles come out. Oops, sorry. But anyway, that's how you draw one. Okay, so how do we interpret this? The way I like to think about it is if the sign of the angular acceleration, the rate at which my angular velocity is changing, if it's positive, what that I'll say is that omega is becoming more positive. And if it's negative, then we'll say that the angular velocity is becoming more negative. Now, what do I mean by that? Let's go and take a look at the two possibilities we could have for angular acceleration being positive. One possibility we can have is that the thing is rotating counterclockwise, which means that the angular velocity is positive and it's speeding up. However, the other possibility would be that it's rotating clockwise, which would make the angular velocity negative. But if it's speeding down, slowing down, then that means that the angular velocity is becoming more positive. You start out with a bigger negative number, you end up with a smaller negative number. That is a positive change to the angular velocity. So either of these cases are possible if the angular acceleration is positive. If the angular acceleration is negative, then our possibilities are that we could be rotating clockwise, which would give me an angular velocity that's negative, and if we're speeding up, we're just heading to ever bigger negative numbers. Or that's rotating counterclockwise, which would mean that omega is positive and it's slowing down. So then you're starting with a big positive number, you're ending with a smaller positive number. That's a negative change to the angular velocity, and so thus the angular acceleration is negative. Where that helps us to tie in is, if you remember, I said that it's also possible that we could have a component of acceleration that's either parallel or anti-parallel to the motion. So let's say, and so this will give rise to what we call the tangential acceleration. Strictly speaking, it's the tangential component of acceleration, but we're lazy in how we say that. So let's say I have a mass on a string. Let's say we're going around at some angular velocity omega, and importantly, we're picking up speed. So just do a quick pause and ponder on this for a second, and ask yourself, we can assume that this is in the horizontal plane. We're going around a circle, we're picking up speed. Which way does the acceleration, not the angular acceleration, the acceleration point? Pause the video and get back with me. Okay, so it turns out that it's going to point inward and forward. And exactly how it gets divvied up will depend on how fast we're going, how big the radius is, etc. But we will have a centripetal component vector here. This is the bit that's responsible for changing the direction, so we're going around a circle. But then since we're changing speed, we also have to have a tangential piece pointing in the same direction as the tangential velocity. And so here I'll go ahead and add them up by the parallelogram method. The actual acceleration of my mass on a string is actually pointing forward and inward. Now, how big is this tangential piece? Since it's responsible for changing the speed, the tangential piece will be equal to dv dt, the time rate of change of the tangential velocity. So this will be the time rate of change of the quantity r times omega, where omega is the angular velocity. Since the radius doesn't change, the time rate of change of the product of these will be the radius times the time rate of change of just the angular velocity. So this will be r times d omega dt. So we get that the tangential acceleration is equal to r alpha. So it turns out that the rate at which the speed of something is changing is directly proportional both to the radius of the circle you're going around in and the rate at which the angular velocity is changing. So to make this maybe just a little more concrete, let's imagine that we have a car that's going around in a circle. So, and we'll say it's a pretty fast car. So I'll have it go around in a quarter of a circle like so. We'll say that a grand total of 5 seconds elapsed in the process. And we will say that we started at rest and we ended up going at at 50 meters per second. And we'll say that the radius of curvature of our road is 100 meters. All right, so let's go ahead and find the acceleration right here at this point. We'll assume it's still continuing to pick up speed at the same rate. So following a clue from what we had before, we know that it's going to be inward and forward because we're picking up speed. So we can just say that the tangential acceleration, since the rate of change, so dv without a vector dt, so this is the rate of change of the speed, since it's changing uniformly, I can say that this is the same difference as the average tangential acceleration, the average rate of change of the speed. So this will be 50 meters per second over 5 seconds is 10 meters per second squared. And to get the centripetal piece, we'll go ahead and say that that's v squared over r. So my final velocity here is 50 meters per second, quantity squared, over 100 meters. That works out to be 25 meters per second squared. So it's going to look something like, acceleration is going to look something like that. And I can break it into a tangential piece of 10 meters per second and a centripetal piece of 25 meters per second squared. That's supposed to be directed towards the center of curvature. Sorry, I made a hash of the artwork there. Let's try that one more time to make it look a little less awful. Yeah, something like that. And we will make my center of the road look a little better too. There we go. Much better. So if we wanted to, if we were using a conventional up, down, right, left coordinate system, so plus x plus y like that, we could ultimately then say that my acceleration was equal to negative 10 meters per second squared I hat plus negative 25 meters per second squared j hat. Or if I wanted to get the magnitude of it, I could say that the magnitude by the Pythagorean theorem is the square root of the tangential piece squared plus the centripetal piece squared, since they're at right angles to each other. So this will be the square root of 10 meters per second squared squared plus 25 meters per second squared squared gives me 26.9 meters per second squared. Awesome. So in the next video, we'll take a look at situations where the angular acceleration is a constant. So we'll be doing rotational kinematics. We'll catch you over there.